Hello, and thank you for listening to this presentation on a low-cost dynamic seat for enhancing rotorcraft flight simulator fidelity. This work is supported by the Navy SBIR program under topic N68335-19-C-0190. I will provide a brief overview of the needs of the people who build and maintain the trainers that are being used to prepare the naval aviators and warfighters supporting the naval enterprise, as well as our technology solution. First, a few words about us. We are Continuum Dynamics Inc., or just CDI. We are a small company located in central New Jersey, about midway between New York City and Philadelphia, which means we have access to both good pizza and cheesesteaks. Our company was founded in 1979 by Dr. Alan Balanin, and we are currently transitioning to a fully employee-owned company. We have a great technical staff with expertise that ranges from aerodynamics modeling and simulation, aircraft design, and specialized testing support to the development of novel techniques for repair and manufacturing processes. We develop software. Two flagship products are CHARM and CGE that provide comprehensive analysis of rotorcraft systems and higher-end computational fluid dynamics, or CFD capabilities. We license our software and other intellectual property, and we also provide contracted engineering services. You can see here some of our prior customers and collaborators across government, industry, and academia. Our technology is developed to support the flight simulation community. While our technology pull is from the subset of the community focused on helicopter and rotorcraft simulation, this solution approach is applicable to many other training scenarios. Flight simulators are finding more widespread use in pilot training, given that simulators are always available, provide a safe environment to train at edge of the aircraft envelope, and ultimately are much lower cost than the flight time in the aircraft. Naval aviators, in particular the rotorcraft pilots, have additional challenges for shipboard launch and recovery operations. Here, the environment is confined often with less than ideal visibility. The landing platform is moving, and due to the wind relative to the ship, there can be significant turbulence over the landing spot. Building a suitable flight simulator or trainer to replicate the shipboard environment virtually is no small challenge, which is reflected by the cost of an operational flight trainer, OFT, that can be a substantial fraction of the cost of the aircraft itself. Current advances in simulation technology are providing opportunities to expand the capabilities of the OFTs at lower cost. Thus, part of the motivating factors of this technology development is to reduce costs for training the naval aviators and warfighters. When building a pilot trainer, one word that comes up often is fidelity, which has several aspects to consider. First, the mathematical and physics models that drive the simulator must be accurate, which requires data to validate and tune the models. But equally important is how the simulated aircraft response is conveyed to the pilot virtually, and there are several parts to this. Most obvious are the visual cues, typically presented by multiple projectors onto a wraparound screen. Both sound and tactile, touch, cues are important as well, where for a helicopter simulator, vibrations correlated with the rotor noise provide an important cue to the pilot as to the flight state of the aircraft. Finally, there are the motion cues. Basically, how the aircraft moves and accelerates in response to the pilot inputs and disturbances from the environment. Those of you who have been around the flight simulation community know that there has been significant debate over the importance of motion cues to the overall virtual simulation experience, with some saying, yes, motion cues are absolutely necessary, and others saying, these cues are distracting since the fidelity is less than the real aircraft experience, so get rid of them. Rather than engage in a flame war, our focus has been to add motion cueing to a rotorcraft simulator that captures the important characteristics the pilot needs and uses to inform how to control the aircraft without a dramatic cost impact. To this end, there are effectively two options available. One is a motion platform that moves the entire simulation cab, which can be expensive. The other is a dynamic seat, which effectively moves the pilot. Dynamic seat technology has been available for some time, with many commercial options available. But even these commercial systems are expensive, albeit less than a full 6 degree of freedom, or 6 DOF, platform. Our solution has been to use an alternate strategy, which I will describe next. Our solution is the Advanced Body Force Cueing seat shown here. The enabling technology leverages advancements made in robotics and motion control hardware, which allows small, compact, low-cost, motor-driven actuators to be built into the seat chassis that provide force cues to the body of the pilot. Our design integrates 4 actuators in the seat pan and 4 in the seat back, all of which are individually controlled to simulate the seat of the pants effect when the simulated aircraft accelerates due to pilot control inputs and turbulence. Another important aspect of our solution is the body force cueing strategy. The cueing algorithm itself, which is designed to match the motion sensory perception process between the simulator and real aircraft. For this, we have followed a model-based approach for developing cueing algorithms that draws upon research conducted in the 1970s on human self-motion perception. In addition, a seat shaker is used to generate vibration cues, providing additional realism to the overall simulator experience. For those who have been around the flight simulation community for a while, our dynamic seat effectively is an electrically actuated G seat, as opposed to the original G seat that used pneumatic actuation. Our design was evaluated in an initial pilot simulation study in the spring of 2022, where it was found to improve fidelity of the simulation with a change of the simulation fidelity rating, SFR, by 1 to 2 on average for all pilots who participated in the study. Note that the original study was performed using a fixed-base simulation of the V-22, thus the fidelity increase is a measurable improvement compared with the baseline with no motion cueing. Currently, we are gearing up for a second evaluation of the dynamic seat on a small motion platform with visual cues generated from a virtual reality or VR headset. This test will be performed during the first quarter of 2024 and will provide additional insight into the interplay between a conventional 6 DOF motion platform and the body force cueing from the dynamic seat. Finally, an important aspect of our solution is that it can be retrofitted onto any simulator seat. As part of this work, we have developed a design process for implementing the body force cueing actuation in a seat considering the physical characteristics of the seat cushion, among other details. Here is a summary of the advantages and benefits of our solution approach and technology. Body force cueing allows us to capture the motion response due to pilot control actions without the need of a 6 degree of freedom platform, which increases fidelity and provides a better training environment. The solution uses compact actuation to provide the body force motion cues, which has less impact on simulator space constraints, is lower cost, and allows the technology to be retrofitted. Finally, use of a model-based strategy to implement the cueing algorithm allows the solution to be adapted to a range of simulators, including fixed-based and 6 DOF motion systems optimally, and with reduced engineering effort, also allowing costs to be kept down. This chart summarizes the current development status of our technology. The initial prototype was developed and tested within our in-house fixed-base simulation lab starting in September of 2021, where developmental testing has continued more or less through the present day. The initial pilot evaluation was performed in April of 2022, which provided not only pilot feedback, but allowed us to identify and correct several technical issues, leading to the current implementation that was shown earlier in the presentation. As noted before, we are gearing up for a follow-on pilot evaluation of the current, enhanced version of the dynamic seat, which was originally planned for December of 2024, but has been delayed due to technical issues integrating the seat within the Motion SimLab facility, but will happen soon. We are near the end of our original Phase 2 and are looking to continue to develop and test the body force dynamic seat technology in other helicopter pilot trainers. Our initial testing has been within the V-22 simulators, within the NavAir Manned Flight Simulator facility in Southern Maryland. Our seat can be applied to any simulator, but is most applicable to helicopter simulators, where motion or body force cues are more important, especially during shipboard launch and recovery. So, platforms such as the H1, H53, and H60 could benefit from the technology. Ultimately, we would like to transition this technology to the fleet trainers as part of a new build or trainer technology refresh, and therefore would like to identify a transition advocate within PMA 205, for example. Given where we are in the development process, we would be ready to start to focus on technology transition once our second Phase 2 pilot evaluation is complete. Since the technology has general applicability to all flight simulation, we are also interested in identifying transition partners across the DoD flight simulator enterprise. We would also welcome connecting with the simulator developer primes, as our technology could provide a beneficial component to new simulators or existing simulator upgrades. Finally, please reach out to us about this or other technical problems and solutions. We have an unofficial motto at CDI. Yeah, we can do that. One that we often remind ourselves when proposing new work. In other words, read the mug. As indicated back at the beginning of the presentation, CDI has done a lot of work developing and integrating software modules that bring higher fidelity physics models to the real-time pilot-in-the-loop simulation world. Some examples are illustrated here, including modeling the complex aerodynamic environment and interactions between the aircraft wake and ship air wake, the aircraft-to-aircraft vortex wake encounters in formation flying, and obscuration due to sand and dust entrainment by the rotor outwash, causing brownout. All of these examples have a common thread: modeling complex aerodynamic phenomena and interactions with the environment accurately and in a manner compatible with real-time simulation requirements. Once again, we'd be happy to discuss your specific problems and needs and work with you to find a solution at any time. Thanks for listening to this presentation.